So you think you know the states of matter, solid, liquid, gas, right? Well, what if I told you that's just the tiniest tip of a colossal iceberg? The universe is filled with a staggering zoo of materials, and physicists have figured out a surprisingly elegant way to make sense of it all. Right, this is where we all start. It's a nice, simple, tidy picture of the world. And it's a great foundation, don't get me wrong, but it turns out it's just the first page of a much, much bigger story.
Yeah, you know the drill. Solids hold their shape, liquids take the shape of their container, and gases just expand to fill up whatever space you give them. Simple, clean, and for a long, long time, this was pretty much the complete picture.
But the reality? Oh, the reality is so much weirder and cooler and just messier. We've since discovered quasi-crystals with symmetries that were thought to be impossible, superfluids that flow with zero friction, and literally dozens of different types of liquid crystals. Then you've got things like spin glasses, bizarre quantum states. Heck, physicists now talk about different states of the vacuum itself. The classic three have exploded into an absolute multitude.
So with this overwhelming variety, where do you even start? I mean, how do you possibly create a system that can classify all this stuff? Not just the materials we know about, but the ones we haven't even found yet.
Well, physicists came up with a system, a really powerful four-step framework that brings order to all this chaos. You can think of it like a universal guide, a map for navigating any state of matter. And that's the map we're going to follow today. So here it is, our 4 steps. First, you have to identify what symmetry was broken. Second, you define something called an order parameter to describe the new state. Third, you look at the wiggles, the little disturbances in that order. And finally, fourth, you classify the unavoidable flaws, the topological defects. Let's take them one by one. Okay, let's dive in. Step 1, break the symmetry. And to really get this, we kind of have to rewire our brains about what symmetry even is. So let me ask you a question. Which of these do you think is more symmetric? A perfect, beautifully structured crystal of ice, or a completely jumbled, disorganized puddle of water? Now, your gut reaction is probably screaming the ice, obviously. I mean, look at it. It's got that gorgeous repeating pattern. You can rotate it by 60 degrees, and it looks exactly the same. A snapshot of water, though? It's just a random mess. No obvious symmetry at all. Well, I'm here to tell you, your gut is completely wrong. And this brings us to a huge idea in physics, spontaneous symmetry breaking. See, water as a whole phase is perfectly symmetric. You can take a bucket of water and rotate it by any angle you want or slide it in any direction. It's still just water. It has complete symmetry. But the moment it freezes, it has to choose an orientation for its crystal structure. And in that act of choosing, it breaks that perfect continuous symmetry it had before. So strange as it sounds, that chaotic-looking liquid is actually the more symmetric state. Wild, right?
So that leads us right into step 2, define the order. A symmetry has been broken, a choice has been made, but how do we describe the new, less symmetric state that's left behind? We need a new kind of variable for that. And that variable is called the order parameter. For a magnet, it's pretty simple. It's just an arrow telling you which way the North Pole is pointing. For liquid crystal, it's like a line that tells you how the long, skinny molecules are generally aligned. For a crystal, it's a measure of how the atoms have shifted away from their perfect grid positions. Each of these parameters lives in its own abstract mathematical world, a kind of map of all the possible ways that order can exist. Now, here's the crucial part. The order parameter isn't just one single value for the entire material. No, it's a field. It can be different at every single point. This is why a random chunk of iron isn't a powerful magnet. All its little magnetic domains, its little order parameter arrows, are pointing in different directions all over the place. Which brings us to step 3. See the wiggles. We have this ordered state, described by this order parameter field. So what happens when we poke it? What happens when we disturb that order just a tiny bit? This quote just perfectly captures the consequence of all this. I mean, stop and think about it for a second. Why is your chair solid? It's amazing. You push on a few atoms on one side, and literally billions of atoms away, other atoms move in perfect, lockstep unison. That's a direct result of the underlying order, of that broken symmetry. Now, there's a deep principle for this called Goldstone's theorem, but all it really says is that whenever you break one of these smooth, continuous symmetries,
You automatically create these long, slow, low-energy wiggles in the order parameter. These collective ripples that slosh through the entire material. They aren't just some mathematical quirk. We can actually perceive them as real phenomena. And we see these wiggles all over the place. In a crystal, those wiggles in the positions of the atoms are what we call sound waves. In a magnet, wiggles in the magnetic direction are called spin waves. And in a superfluid, this is my favorite, they actually manifest as waves of temperature. Physicists call it second sound. How cool is that? And that brings us to our final step, where things get really wild. Step 4, find the flaws. Because no matter how perfectly ordered a material tries to be, there are always mistakes. There are always tears in the pattern that are impossible to just patch up. These are called topological defects. A classic example is a dislocation in a crystal. It's like you have an extra row of atoms that just ends right in the middle of the grid. You can't fix that just by shuffling a few atoms right near the mistake. The problem is global. It's locked in by the overall structure, by the topology of the whole thing. And this is not just some abstract idea. You've totally felt this. Ever take a paperclip and bend it back and forth a few times? The first bend is easy, but it gets harder and harder to keep bending it. That's called work hardening. What you're actually doing is creating and tangling up trillions of these topological defects, these dislocations. They form this microscopic traffic jam that gets in the way of other defects moving around, and that's what makes the metal feel stiffer. You are literally feeling a tangled web of imperfections. So this leads to a really profound question. You have these defect lines running through the material. What happens when two of them try to cross each other? Can they just pass right through, or do they get stuck? And the answer, incredibly, depends on the deep mathematical rules of their order space. If the defects are what we call commutative, meaning the order of operations doesn't matter, like how 2 times 3 is the same as 3 times 2, then they can pass right through each other. But if they're non-commutative, where the order does matter, they can't. They become topologically entangled. They braid around each other and are fundamentally locked together. And this is not just a theory. This exact principle, braiding these non-commutative defects that can't untangle themselves, is one of the most promising ideas we have for building a robust, fault-tolerant quantum computer. The idea is to encode information in these topological knots because the topology itself protects the information from noise. So we've gone from a simple puddle of water all the way to the absolute frontier of computing. It all comes down to this powerful way of understanding the beautiful and complex multitudes of matter.